The binomial theorem. So when we're looking at binomials and we take them to powers, interesting patterns occur. So for example, if we take x plus y to the 0 power, we get 1. X plus y to the first power, we're just going to get x plus y. But then as we move on down, x plus y squared, we can see symmetry starting to develop. So we have a 1, if we look at just the coefficients, a 1, a 2, a 1. Here we have a 1, 3, 3, 1. And over here, if we take x plus y to the fourth power, and we do all of the distributing, we're going to end up, after combining like terms, with a 1, 4, 6, 4, 1. So it's got a nice symmetry there. And Pascal actually discovered the symmetry of these polynomials. This symmetry isn't only in polynomials, we also have this symmetry showing up in probability. So Pascal's triangle, if you look at it, it's got ones down the sides, and then you've got the same sort of symmetry going on between. So we have a 1, which is to our 0 power. This is the 0th degree. The first degree, we have a 1 and a 1, and then a 1, 2, 1. Now if you notice, if we take the ones right here and add them together, we'll get a 2. Here, this 3 can be found both up here in our taking to the third power, and also the 1 plus the 2 on the row above. This one as well. So this is my third degree. Now the tricky part about Pascal's triangle is you have to remember that you're starting with that 0th degree, and anything to the 0 power, remember, is 1. Here again we can see 1 plus 3 is 4, 3 plus 3 is 6. We could continue on down, and this would be a much easier way than distributing all those x's and y's. Also, when looking at these patterns, I can see my variables changing. If I look, for example, at x plus y to the third power, when I'm expanding it and combining like terms, notice I start with just an x cubed. And my y is to the 0th degree here, which just makes it a 1. Here, I go down 1 by 1 power, x squared, x to the 0. At the same time, my y variable is going up 1. So starting here, y to the 0, y to the first, y to the second, and y to the third. The same is true with all of my different degrees here. If I take it to the fourth power, I start high with x to the fourth with the highest power, and I go down by 1, and with y I start with y to the 0 and go up by 1 until I get to y to the fourth. And this is true with every expansion. You can see that if we add the exponents together, x to the third plus y, we're always going to get that fourth power. So we can use Pascal's triangle to expand something that looks like this, 2x minus 3y to the fifth power. Now that would take a long time if we wrote that out 5 times and distributed. But using Pascal's triangle, I can expand this in a much easier way. It looks pretty complicated, but it would take a lot longer to expand it, writing that 5 times and distributing. Now before I had an x plus y. In this case, my 2x represents that first term, and my negative 3y represents the second one. So when I expand it, I'm going to start with that highest power, and I'm going to use these as my coefficients from Pascal's triangle. So those are written in green. So I have a 1 right here. Now 1 times anything is itself. I just wrote the 1 so that you could see it from up here. And then I'm going to take this first term and I'm going to take it to the fifth power because I want to use the highest power there. And I have a negative 3xy to the 0 power. Now you don't have to write that when you're expanding it because we know anything to the 0 power is 1. I just wanted you to see this going up by 1 power every time. So then I have the 5 over here from my Pascal's triangle, the 2x to the fourth power minus 3y to the first power, plus 10 from over here, 2x to the third, going down by 1 power, and negative 3y squared, going up by 1 power. Again, the 10, 2x squared, negative 3y cubed, plus a 5 from up here, 2x to the first power, negative 3y to the fourth power, and my last one, I've got my 1 here, 2x to the 0 power, negative 3y to the fifth power. So then, just combining everything in here, I have 2 to the fifth. Remember, when you have something to a power, you have to take both of those to the power. So this 2x to the fifth is not 2x to the fifth, it is 2x to the fifth. So I have to say that that's 2 to the fifth times x to the fifth. And I just multiplied that by 1, and so I don't need to write that anymore. Same here, and I just gave the power to both of the things I'm taking the power to. And I did that all along here. And then I went ahead and calculated those powers. So 2 to the 5th is just 32, x to the 5th. Now notice when I take this negative 3y to an odd power, it's going to be a negative number. So for example, I have 2 to the 4th, which is 16, times negative 3, because this is to the first power. So that's where my negative 48 came from. I still have my 5 from my Pascal's triangle. Plus 10, 72, I just took 2 to the 3rd, and negative 3 squared. Negative 3 squared is going to give you a positive 9, times an 8 is 72. Same thing down here. Notice I have a negative number because I have negative 3 to the 3rd power, so that's a negative 9. Multiplied them together all the way down here until I get to negative 3 to the 5th power, which is going to also be a negative number. So that's negative 243 y to the 5th. And then I just multiplied. And you can use a calculator for this. I mean, I guess you could do it by hand. Some of them are pretty easy. But I just multiplied them all together, noticing that my odd powers of y is going to give me a negative number. Now, if x were negative, it would be my odd powers of x that would give me the negative number. So then just expanding, and then I have this binomial expanded without even having to distribute. So if you were to expand it all, this is what you'd get. And if you really don't believe me, you should try it. Make sure you get the same answer. Now to do this next part, we need to remember a bit about factorials. And maybe you learned about factorials or maybe not, but it's a pretty easy operation, something you've probably seen, probably in probability actually. And we have this little spider hanging off here, kind of wanting to learn a little bit about factorials too. So I'm just going to leave him there. So 6 factorial, that factorial is an operation. It tells us to do something with that 6, much like addition or subtraction or multiplication. So when I say 6 factorial, it doesn't mean like, yay, 6. It's not like an exclamation point, but that is an actual operation. And you can find it on most scientific calculators. 6 factorial is just equal to 6 times 5 times 4 times 3 times 2 times 1. So you're just going down by 1 every time. So you can do that with any whole number where you can just multiply down by 1 every time. So because factorials are operations, that means you can't just cancel the factorials. Just like if you had a problem like this, you couldn't say plus over plus equals 1. So when you have 6 factorial over 4 factorial, you can't just cancel the factorials and say that's the same as 6 over 4, because it's an operation, just like you can't cancel plus over plus. So 6 factorial, though, you can make it a little bit easier. 6 factorial over 4 factorial. 6 factorial equals 6 times 5 times 4 times 3 times 2 times 1. 4 factorial equals 4 times 3 times 2 times 1. And oftentimes we won't write the 1 because anything times 1 is itself. So you don't have to write the 1 in there. I'm just showing you that by definition. Now if we look over here, we can see that we have 4 times 3 times 2 times 1, 4 times 3 times 2 times 1. So it would be okay to cancel those. We could cancel these right here because we have a 4 over 4, which gives us a 1, a 3 over 3, a 2 over 2, and a 1 over 1. That's all 1 right there. That's just a big fancy 1. So here, we could actually rewrite 6 factorial as 6 times 5 times 4 factorial. So this right here is 4 factorial, and it's over 4 factorial. So 4 factorial over 4 factorial, we can make a 1 out of. We can't just do that with the exclamation points, but we can do that with a 4 factorial over 4 factorial. And that gives us a 1. So 6 factorial over 4 factorial equals just 6 times 5. 6 times 5 is 30, so if you had to do that calculation. Now, why, you say, are we learning about factorials? Well, there's an even easier way to use the binomial theorem and to use that expansion to find a specific term. Like say you didn't want the whole expansion, you only wanted the 4th term or the 5th term. There's an easier way than even using Pascal's triangle. Okay, so say you wanted to find the 3rd term of 2x minus 3y to the 5th power. Well, we already know the 3rd term, 1, 2, 3, because we did the expansion. But there's an easier way we could calculate a single term if we wanted just a term instead of the whole expansion. Of course, we could do the whole expansion and then find the 3rd term, but it gets pretty messy when you get to like something to the 12th power. And so here's a formula that was developed in probability. Now this formula has lots of parts and pieces. Let's just go ahead and kind of take it apart a little bit. But it's n factorial over k factorial times the quantity n minus k factorial. And it's important that that n minus k is in parentheses, so don't forget that when you're copying that down, because we want to take the factorial of this quantity, not of n minus k factorial. It's the whole thing factorial. A to the n minus k, b to the k. So n is just the degree of my polynomial. So in this case, my degree is 5. So n is going to be 5. A is going to be my first term of the binomial. So in this case, it's going to be 2x. B is going to be my second term. My second term is negative 3y. And the reason is because I could rewrite this as 2x plus negative 3y. So my b is going to be negative 3y. Now if we look at this k, where this mysterious k comes from, we know my second term is going to be to the k power. So my second term of this binomial. So I'm looking at that negative 3y. I'm looking really at my y variable. So if I look over here, and I look at my second term, in this case it's going to be to the second power. Notice my x is going to take on the value, that third power. So this second power is related to this third term by minus 1. So if I want to know k, I'm going to take what term I want the third term, and I'm going to subtract 1. So in this case, my k is going to be 2. If I wanted the fifth term, then my k would be 4. But in this case, my k is 2. Now notice if I take the degree minus k, I'm going to get to the third power. So if I take 5 minus 2, I'm going to have my a to the third power, which is what I want for the third term. Now let's go ahead and put in our values and kind of check out how this formula works. So I take 5 factorial, because I'm taking my n, my degree n, 5 factorial over 2 factorial times the quantity of 5 minus 2 factorial. And then I have my first term, 2x, to the 5 minus 2 power, which is going to be 3, but I just left it at 5 minus 2 there. And then I have negative 3y to the second power. That's going to give me a positive value right there. Now let's go ahead and simplify it. I want you to notice that this is written in green. And that's because this part of the formula gives you that part of Pascal's triangle. So since we're looking at the third term, we expect this value to be a 10. So then over here we have 5 factorial over 2 factorial times 3 factorial. That's just 5 minus 2. And then I went ahead and cubed both the 2 and the x. So I have 2 cubed, which is 8, x cubed. And then over here I squared both the negative 3 and the y, which gave me 9y squared. Then I went ahead and expanded my factorials a little bit. I took 5 and I did 5 times 4 times 3 factorial. And I stopped at 3 factorial here because I know my largest factorial in the denominator is 3. So I have 3 factorial, and right here, instead of writing 2 factorial, it's just 2 times 1, so I just wrote a 2. So 5 times 4 times 3 factorial over 2 times 3 factorial. Well, I know 3 factorial over 3 factorial is just going to give me a 1. And then I have 5 times 4 over 2. Now if I take that 2, I can go ahead and take a 1 out. I can divide this by 2 and divide this by 2. So then I just have a 5 times 2, which is 10. And that's exactly what I expected over here from my Pascal's triangle. So I have 10 times, and I put my coefficients together, at 8 times 9, and I have x to the third, y squared. Multiplying that all together, I have 720 x to the third, y squared, which is exactly what I got up here by expansion. Okay, so let's try one last example. Find the 7th term of x minus y to the 12th. Now you really don't want to expand the 12th. I mean, we could use Pascal's triangle and go all the way down to, it would be the 13th row, remember, because we start at 0 and go all the way down. And we could do that with Pascal's triangle, but you have to have a lot of paper. But we're going to try just using this given formula. So n factorial over k factorial, n minus k factorial. Remember, that gives me the coefficient in Pascal's triangle. A to the n minus k, b to the k. So in this case, well, in every case, n is the degree, but in this case the degree is 12 because I'm taking it to the 12th power. A is the first term, so if I look up here, my first term is x, so a is x. B is my second term. In this case, it's negative y, because remember, I can rewrite this as x plus a negative y. And k is going to be the term I want, which is the 7th term, minus 1, so going to be a 6. So then I'm going to substitute in all of my values. I have n factorial, which is 12 in this case, so 12 factorial, over k factorial, k6, times n minus k factorial, so 12 minus 6 factorial, which is going to be 6 factorial as well. And then I have x to the 12 minus 6, my n minus k, and negative y, don't forget that negative there, negative y to the 6th power. In this case, it's not going to matter because I have an even degree, so that's going to be a positive number. So I have 12 factorial over 6 factorial times 6 factorial. So I have times x to the 6th, y to the 6th. So then expanding this, I can see I've got to go all the way down until I hit 6 factorial here, because then I have a 6 factorial over 6 factorial, which will give us a 1. This 6 factorial, I'm going to have to expand. I can't make a 1 out of both 6 factorials. It's just 6 factorial over 6 factorial. I still have this 6 factorial right here. I have this right here. And then these make a 1. I still have the x to the 6th, y to the 6th. You can see I kind of forgot to write it in there, so I had to squish it in there. But it's still times x to the 6th, y to the 6th. Here this makes a 1. I just have 12 times 11 times 10 times 9 times 8 times 7 all over 6 times 5 times 4 times 3 times 2 times 1. But I don't have to write the 1 there because anything times 1 is itself. And then I have the x to the 6th, y to the 6th. Then I can go ahead and make some fancy ones to make this a little bit simpler. So here with my 6, I have a 6 on the bottom. I take a 6 out of the 12 and I have a 2. I have a 5 and the 10. So I have a 2 up top and a 1 on the bottom. A 4, and then I have a 2 here, right here on the 2. So you have to imagine that that's not there yet. And then I have the 3 and the 9. And I have a 3 on top and a 1 on the bottom. And then this 2 and this 2 is going to give me another 1. So that simplified it a whole lot. And now I have 2 times 11 times 2 times 3 times 7 times x to the 6th, y to the 6th. So that just gives me 924 x to the 6th, y to the 6th. And I didn't even have to expand this or multiply x minus y 12 times.